complete randomized design, which is CRD. There are two sources of variations among a number of observations obtained from the CRD trial. The one is the experimental variation, or treatment variation, and the other one is experimental error. So this the treatment variation and the experimental errors are considered as the two sources of variation in the CRD experimental design. And the relative size of the two is used to indicate whether the observed difference among the treatments is real or due to chance, and thus the treatment difference is said to be real if the treatment variation is sufficiently larger than that of the experimental error. So if the difference between the treatments is greater than that of the experimental error, just we can say that the difference is real, whereas less than the experimental error, just it's due to chance. That means, so experimental error measures the variation that exists among the observations in the experimental is treated alike, and the variations could come from the two main sources, from the inherent variability, that means natural variability, and the results from any lack of uniformity in the physical conduct of the experiment. In case of inherent variability with the experimental material to which treatments are applied, it may be arise from plant to plant variation, or its treatment variation, and also plant variability. That means the treatment, it might be if our treatments are varieties, just the variability between plants considered to be the inherent variability, whereas the seasonal variability, soil fertility, soil variability, fertility, slope, pH, and also temperature and sunshine, and the last wind is considered as the inherent variability arise from the experimental materials are considered to be inherent variability. In the other case, there are also causes for lack of uniformity in the physical conduct of the experiment, like applying treatment, taking measurements, and this kind of variations could occur due to mistakes, slopeness, and random outcomes like flooding and insect outbreaks are considered to be the sources or the cause for the other or maybe artificial variability, which is not inherent. That means, so when we see the experimental error can never be eliminated completely, but can be minimized, and a good experimental design minimize error so that the treatment effect can be detected more readily. And when we see the ANOVA in CRD, there are two cases: the CRD with equal replication with no missing value, that means, and also there is also another CRD with unequal replication or missing value. So in two cases we can estimate, or we can conduct ANOVA. So in case of CRD with equal replication, the ANOVA with equal number of replication of the treatments, we have steps also. Just the first step in this case is grouping the data by treatments and calculate the treatment totals, the grand totals, and also the treatment mean and the grand mean. So to find the treatment total, just we have to, the treatment mean, just we have to divide the treatment total for replication, whereas to find the grand mean, just we can divide the grand total into number of observations, that is that can be found by multiplying number of replication by the treatment. The second step for ANOVA in the equal replication is constructing the outline of the ANOVA table or the ANOVA layout. Here it is the ANOVA layout for CRD design. Just here are the source of variations, treatment and experimental in case of CRD. Here are also the degree of freedom, sum square values. Here also mean square values, and F calculated, F tabular. This tabular value is obtained from F distribution in the appendix table, and just by using the treatment degree of freedom and the experimental error degree of freedom, just we can read the tabular value at 5 and 1 level of significant level. Here, just this is all about the outline or the skeleton of ANOVA, and the third one is calculating the degree of freedom for each source of variation. That means just after we have set the outline, just the next could be just estimating or calculating the degree of freedom for each source of variations. So treatment source of variation, treatment degree of freedom is here. The first could be, so in order to obtain this, you just subtract 1 from the number of treatment, that means t minus 1. Whereas the experimental error degree of freedom, just we can use this formula t into r minus 1 and substitute the numbers. Just you'll give us the experimental error for CRD, and also you can obtain also error term or experimental error degree of freedom by subtracting the total, the treatment degree of freedom from the total degree of freedom. Just you can get error degree of freedom by 2 methods, either subtracting treatment degree of freedom from total degree of freedom or by using this formula. And the fourth step is calculating the correction factor or CF and the other sum square values for each source of variations. In order to obtain correction factor, you have to square the grand total and divide the total number of observations, that means replication times treatment, and also the total. Then we have to calculate also the total sum square values in order to obtain this total SS or total sum square values. First, you have to square all observations and then sum, and next subtract correction factor from the summation of all squared values of total observations. That means then you have to find also the treatment sum square values, treatment SSS. Just in order to obtain these treatment sum square values, just we have to square all the treatment totals and sum. Then the sum values will be divided for replication, number of replications, and subtract correction factor from this value. That means then after we have got those values, just you can estimate also error sum square values. To obtain this treatment error sum square values, just subtract treatment sum square values from total sum square values. That means so this is the fourth step, and the fifth step is calculating the mean square values for each of the source of variations by dividing each sum square values by its corresponding degree of freedom. For example, for treatment mean square, just you have to divide the treatment sum square values into its degree of freedom, that means t minus 1. Whereas error mean square is obtained by dividing or dividing error sum square values by its corresponding degree of freedom, that means error degree of freedom t into r minus 1 in case of CRD. And then after we have got the mean square values for treatment and error mean square values, just we have to calculate the F values or F calculated values for testing the significant treatment difference. F calculated is obtained as by dividing the treatment mean square value for error degree of error mean square values. Just we have calculated the treatment mean square and error mean square values. So by dividing this value with this value, just we can obtain F calculated value. And then we have just after we have got F calculated value, just the next step is obtaining the tabular value, the tabular F value or F tab value by using the treatment degree of freedom as numerator and error degree of freedom as denominator at 5 and 1% of significant level. And then the next step is comparing the tabular value and the calculated value with that of the tabular value, and decide on the significance of the difference among the treatment using the rules. The first is rule A: if the calculated or F calculated value is greater than that of the tabular F value at 1% significant level, just the treatment difference is termed to be highly significant. That means there was or there were highly significant difference between the treatments. That means, and then you or designate that the two asterisks, here it is, and or putting the two asterisks at the calculated value of F in the ANOVA table. And the second rule is if the F calculated value is greater than that of the tabular F value at 5% level of significance, the treatment difference is said to be significant, and put one asterisk at the calculated value on the at the calculated value of F in the ANOVA table. Whereas if the calculated value is less than that of the tabular value at 5% significant level, and the treatment difference is said to be non-significant or insignificant, and use the designation NAS at the calculated value of F at ANOVA table. And the next step is calculating the coefficient of variation. Just after we have got all the values which are found in the ANOVA skeleton, just we have to calculate the CV value, and we have to put the CV value at the or below the ANOVA table. Therefore, in order to find the CV value, just we have to divide the root mean square value of error for grand mean and times to 100. That means by 100. Then we have to go to the CV in percent. That means, so this value indicates that the degree of precision with which the treatments are compared, and it's a good index of reliability of the experiment. That means the higher the CV, the lower it's the reliability of the experiment, whereas the lower the CV, and it indicates the higher the reliability of the experiment. And the CV value is always placed below the ANOVA table, and the CV value is variably acceptable. For example, in case of Gomez and Gomez, CV for valid trial is accepted from 0 up to 8%, and for fertilizer trials from 10 up to 12% is acceptable. Whereas for insecticide and pesticide trials from 13 up to 50% of CV value is acceptable. But when we review and see different literatures suggest that in field experiments, CV up to 30% of for field experiment is tolerable, and the lesser the CV is expected from the laboratory and greenhouse experiments, because the variation in the laboratory or the environmental or source of variation in the laboratory and the greenhouse experiments are lower that of the field experiments. That's why the larger or moderate CV is acceptable or tolerable in the field experiments than that of the experiments conducted in the laboratory. When we see the example here, the nitrogen content of our bean inoculated with 6 rhizobium strains with 5 replications, the plot number is assigned by numbers from 1 up to 13, and the treatments are designated by letters, whereas the nitrogen content in the parentheses. That means here the table are the values. For example, we can see that this box is designated as 1, and the next 2 up to 30. Those boxes considered as experimental units, and the values from 1 up to 30 is given for the number of experimental units. So in general, just we have 13 experimental units, and also from the first experimental unit there is treatment. The first treatment, that means treatment A, and here in the bracket is the value of nitrogen content, that means for that given treatment A, whereas here are also the values for nitrogen content and the respective treatment E. That means, so if we have such kind of data, just we have to follow the steps in ANOVA procedure. That means the first is arrange or group the data by the treatment and calculate the treatment totals, gram totals, and treatment mean and grand mean. First, we have to just arrange the data by treatment wise and the replication. here there are what 6 treatments, 1 2 3 4 5 6 A B C D and E F treatments, and also here are what the replications from 1 up to 4 replication. So A is replicated 5 times. Just you can find in this from 30 experimental units, treatment is assigned in 5 experimental units. That means just the first one is here, treatment A, replication 1, and treatment A, replication 2, and treatment A, replication 3, treatment A, replication 4, that's 32.1, and the replication 4, and replication 5 treatment A is just found here in the 29th plot number, and the value or the nitrogen content for this treatment, the last treatment, is 33.0. All the other treatments should be arranged similarly in the treatment A fashion, and then we can also the next step is what estimating or calculating the treatment total and the grand total. So you have to sum up all the values from the first replication up to the fifth replication, and then you will get the value 144.1 for this treatment total. And the second treatment is similarly when we sum all these values in the replication wise, just we will have 119.9. This is the second treatment total, and the third treatment total similarly up to 5 the 6 treatment totals. And if you sum also these values, just we will obtain also the grand total as indicated here, and also we can sum all these observations and it will give us similar values like this. The better one and the easiest one is summing up the treatment totals in order to obtain the grand total. When we see the grand mean, just we can divide the grand total into the number of observations. That means by multiplying the replication with its treatments. We have 5 treatments, and each of them we have 6 treatments, and each of them replicated 5 times, and we will have 30 observations, and by divide this one into this one, just we will obtain this value. The second step is calculate the degree of freedoms for all sorts of variations by using n-1, and the third step is calculate the correction factor in sum square values as follows. Correction factor is equals to squaring the grand total and dividing the number of observations. Just so when we square this value, that we have obtained from the table the grand total, and also square this value and then divide by this value. That means this is what the replication and number of treatments, and we will have this value as correction factor. After we have obtained the correction factor, just we have to continue to estimate total sum square values, TSS. In order to obtain this value, just we have to square all observations and sum each observation, and then subtract safe value, and we will obtain that is this value. For example, to obtain this one and all observations, that means starting from 19.4 here, 19.4 up to squaring all observations from this up to this value, and sum all their square values. After we have got the squared sum values of each observation, we have to subtract correction factor in order to obtain total sum square values, and we'll have also this value. The next step is estimating the treatment sum square. In order to obtain this one, we have to square and sum the treatment total values and divide by replication and minus correction factor, and it measures the variability between the treatment. In order to see this, just treatment sum square value is equals to squaring the first treatment A total square, that means 144.1 square, plus treatment 2 or treatment B total, treatment total square value, that means 119.2 square, plus the sixth treatment or treatment F, that means 93.5 square value, by dividing this sum value with that of replication of 5 and subtract from this correction factor, then we can obtain or we can get that treatment sum square value. Then after we have got the total sum square value and the treatment sum square value, just we can estimate also error sum square values. In order to get this, just subtract treatment sum square value from total sum square value. So we have total sum square value, this one, and we have treatment sum square value, this one. Just if you minus or subtract this value from this value, that means this value from this value, just we can obtain 282.993. This is the value of error sum square values. The fourth step is calculating the mean square values. After we have got all the sum square values, just we have to divide each sum square values by its corresponding degree of freedom. Therefore, treatment mean square value is equals to treatment sum square value by its divided by its degree of freedom, treatment degree of freedom, meaning, so if you just divide this value by this, just we can obtain this one. Similarly, error sum square and mean square is equals to the value of error sum square divided by error degree of freedom. This is what error degree of freedom for CRD, not the other designs. This is, we are doing an experiment conducted in the CRD, that means, so just we have to use the degree of freedom for that design, that means, so in this case we have to use the CRD design, and the calculation is also used as the design concerned, that means. So just if we do similarly this, just we will obtain 11.79, that means. Then after we have got the treatment mean square values and error mean square values, just we have to find the calculated F value for testing significance of treatment effects. Treatment F calculated is equals to treatment mean square value over error mean square values. Just this is what the treatment mean square value is calculated here, and also error mean square value is calculated here. So in order to, if we calculate or estimate or divide this one by this one, just we can obtain F calculated value is this, or 14.37, that means. And the next step could be obtaining the tabular F value by using treatment degree of freedom as numerator and also error degree of freedom as denominator at 5 and 1 level of significance, that means. In this case, just we have 6 treatments and the treatment degree of freedom could be 5, that means 6 minus 1 is 5, whereas we have also 24 error degree of freedom. We can see yeah, t into r minus 1, we have 6 treatments and 5 replication is just 5 minus 1, 6 times 5, 30 minus 30 minus t, 6 minus times 1, 6, therefore 30 minus 6 gives us 24, therefore error degree of freedom could be 24. Okay, so we have to use we have to read by using F calculated from F distribution by using 5 error degree of freedom and treatment degree of freedom and 24 error degree of freedom at 5%, and we will have 2.62 value and similar values, and 1% 0.90 is 90, that means. To show you this value, look, remember that treatment degree of freedom is 5, whereas error degree of freedom is 24 for both cases, for at 5% and 1%. And we will see the values at each degree, level of significance at 5% and at 1%. Look and remember this. If we go to the F distribution table, yes, we have to use that. In case F distribution at 5%, we are now at 5%. Therefore, here are this direction, or in the horizontal direction, just you have to use the treatment degree of freedom as numerator. So in our case, we have 5 degree of freedom, treatment degree of freedom, and 24 error degree of freedoms. So therefore, we go downward. Here is the error degree of freedom, and go 5 times 1, 2, 3, 4, 5. So at 5% level of significance, the F tabular value by using 5 treatment degree of freedom and 24 error degree of freedom, just the value is 2.62. So we can check this value at 5%, 2.62. Really nice. And when we go to 1%, it is we can obtain, or we can get the value 3.90 at F distribution. Check, we can check. This table is at 5%, and the next step is the next table is at 1%. So we have to see the value similar treatment degree of freedom and error degree of freedom, but at different level of significance. That means at 1%, and we can check that one, 5 and 24. The intersecting point could be used. Therefore 24 downward, and 24 and 5, 1, 2, 3, 4, 5. So the value is correct. So by using similar fashion, just we can obtain at a different level of significant difference in the F distribution table. So this is a procedure how to get the value of these values. That means, and for quick assessment of the results and summarize all the values computed on the above steps, and also submit all the values in the ANOVA table. That means here it is. So we have calculated that the degree of freedoms, and also the total sum square values, sum square values and mean square values, and the calculator values, and also we obtained the tabular values at 5 and 1%, just here in the previous slide. And also we have seen the procedure how we can get F values F tabular values at 5 and 1%. That means, therefore, based on this, just the value that calculated F indicates that there was F calculated was 14.37, whereas the tabular values were 2.62 and 3.90 at 5 and 1% respectively. Therefore, we have to compare these values with this first, and if not, just go to this. And if this value is larger than that of this one, we have to say that there is highly significant difference between the treatments. Whereas if this value is larger than this one, but lower than this one, just we can say that's significant only, and we can use one asterisk. Whereas in case of 1%, just because of this, we have used 2 asterisks, because this value is larger than that of 1%, and in order to say high significant, just we have to put 2 asterisks. After we have got all the values in the ANOVA, then we have to calculate the value of coefficient of variations and put always below the ANOVA table. The CV is calculated as that the root square values of error mean square value, or mean square error values, and by dividing it for grand mean multiplied by 100, we can obtain the CV value, and if we calculate this one, just will give us 17.3 value. So the CV value for this experiment is or was 17.3%. Therefore, with this all values, what conclusion we will give from this ANOVA table, or what conclusions we may generate from this ANOVA table? That means, therefore, in the above example, that means in this example, the value that is 14.37 is greater than that of 3.96 at 1%. This value is greater than this one at 1%. Thus, the treatment difference termed to be highly significant, and we can put 2 asterisks in the F calculated in the ANOVA table. That means here. In other words, chances are less than 1 in 100 that all the observed difference among the 6 treatments means could be due to chance. But 99%, we are sure that 99% the difference is real. That means, so significant if test verifies the existence of some difference among the treatment tested, but doesn't specify the particular pairs or of treatments that differ significantly, because the ANOVA only tells us whether the presence or the absence of significant difference between treatments. Rather, it doesn't tell us the extent or the degree of variations of the treatment pairs. That means which treatment is greater than, or how much greater than with the other treatment. So this information is not obtained from the ANOVA table. Rather, we can obtain by conducting or going to do the mean comparison table. That means, but for our example, this is enough.